Let's talk about the dot product. You'll be able to use the dot product to determine the angle between two vectors or to determine the projection of a vector along a line. You can think of a projection as a shadow. So if you think about a board or something leaning up against the wall and the sun shining down on it, the shadow of that board on the ground is a projection of that board. And we can think of a projection of a vector in a similar way. Now, we are obviously online and will not be able to go through all this, but you should look at the example problems and the group problem solving problems in the slides and follow along with those as examples as well in order to learn this topic. What applications are there for this dot product thing? Well, if we know where the four ends of two cables are located, how would you calculate the angle between those cables? Is there a way you could do it? Actually, that's where the dot product comes in. The interesting thing about vectors is now we don't just have scalars, we have a magnitude and a direction. So how do you perform operations on them, like addition, subtraction? Well, that's pretty easy, but what about multiplication? What about division? Well, I don't know of any division method that is used for vectors. You can, of course, divide a vector by a scalar, but I don't know how you would divide one vector by another. I don't even know what that would mean. But there are actually two ways to multiply vectors. One is called the dot product, and that's what we will study today. The dot product has useful applications like finding the angle between these two cables if you know the position of the ends of the cables. There are other applications as well. If you're applying a force to the end of a wrench or something, and that force is not perfectly perpendicular to the wrench, only a component of the force actually applies torque to the fastener. And so what part of the force is it that helps to actually turn the wrench? Well, the dot product will help us determine that. So what is this dot product thing? How do you compute it? Well, imagine that you have two vectors, A and B, with some angle theta between them. Now, the dot product of those two vectors is defined as their magnitudes multiplied together and then multiplied further by the cosine of the angle between the two vectors. So the dot product is written as vector A dot with vector B, which, as I said, is equal to the magnitude of A times the magnitude of B times the cosine of the angle theta between the two. Now, the angle theta is always whatever the smallest angle is between the two vectors, not moving around some curved surface, but the two vectors A and B define a plane, and so theta is the angle within that plane and always has a number between 0 and 180 degrees. Now, the dot product yields something very interesting. The dot product actually yields a scalar. So basically, you take two vectors, you put it into the dot product, and what comes out is just a number, something that does not have direction. Another interesting feature of it is that the units you get by performing this operation on two vectors, the units is simply the multiplication of the units of the two vectors. So for example, if A and B both had units of feet, then the units of the dot product of A and B would have units of square feet. If you had, I don't know, seconds, well, that's not a good example because seconds are not, I can't think of an example where that would be a vector, but if you had pounds and feet, so vector A is in pounds, vector B is in feet, then the dot product of those two would have units of foot-pounds or pounds-feet, either one. The unit vectors are also vectors. What do you get when you take the dot product of two unit vectors? Well, it depends. It depends on the particular dot products. Notice that I and j are unit vectors along the x and y axes, and so they are perpendicular to one another. So the angle between those two vectors, by definition of the coordinate system, or an orthogonal coordinate system, is 90 degrees. And the cosine of 90 degrees is 0. Therefore, I dot j is 0 because the cosine of the angle between them gives 0. Now, I dot I is equal to 1. Why? Because the projection of I along itself is equal to 1. Or another way to say this is that the cosine of the angle between I and I, which is the same vector, the cosine of that angle, which is 0 degrees, will give you 1. And since I itself has length 1, dotted with the second I, which also has length 1, we basically have 1 times 1 times 1 is 1. Now, another way to calculate the dot product from the components of the individual vectors is to take the two vectors and multiply the common terms together. So if we have AXI plus AYJ plus AZK dotted with BXI plus BYJ plus BZK, all you do is you take the I components and multiply them together. And what you get is AX times BX times I dotted with I. You see, the dot product actually works on the direction part of the vector. And so what we're left with, since I dot I is equal to 1, we have AX times BX times 1, which is just AX times BX. But then you have to do that for the J components as well and the K components, and then you simply add all of those terms together. So you get AX BX plus AY BY plus AZ BZ. That is the dot product of A and B. And so that's the way that you can calculate the dot product from the components of the two vectors. Now, if we want to use the dot product to determine the angle between two vectors, such as those two cables that we talked about earlier, we can find the angle by doing this. First of all, find the dot product between the two given vectors, because, of course, we would have AX, BX, AY, BY, AZ, BZ, because we know the endpoints of those two cables, or in this case, we know the two vectors. Then we could find the magnitudes of A and B, and then use the definition of the dot product to solve for theta. So what we would do is take A dotted with B, divide by the magnitude of A and the magnitude of B, essentially creating the dot product of two unit vectors, and that will give us the cosine of the angle theta. Take the inverse cosine of A dot B over A times B, and there you have the angle theta, which will be the angle between the two vectors. But if what we're interested in is the projection of a vector, we can figure out the components of the vector parallel and perpendicular to a line using the dot product as a tool. So what do? Well, first of all, find the unit vector UA that lies along line AA. How would we do that? Well, it depends on line AA. We'd have to know something about line AA, but let's just assume we can find that unit vector. And then what you would do is find the projection of the vector A along the line AA. In other words, take the dot product of vector A with the unit vector along the line AA. Basically, calculate the shadow of vector A on line AA. And the way you do that is by simply taking the dot product of vector A with the unit vector UA. And so you see that that's what's been done at the end of step 2. We've got AX times UX plus AY times UY plus AZ times UZ. And that number, that addition, whatever you get at the end of that calculation, is the length of vector A along line AA. In other words, the parallel component of vector A along line AA. So we can find that length. Then what? Well, if we need to know that projection, that shadow as a vector itself and not just its length, then all we really need to do is take that magnitude we just found in step 2 and multiply it by the original unit vector, which defines the direction of line AA. And now we've got a vector that is the shadow or the projection of vector A on line AA. If we also need the component of the vector A perpendicular to line AA, we can obtain it. Let me show you how that works. I'm going to go back a couple of slides and let's look at this. If you think about it, vector A looks kind of like the hypotenuse of a right triangle, and the component of A, the projection of A along line AA, in other words, A parallel, that looks like the base of a triangle. And so the height of the triangle would be A perpendicular, okay? And so we should be able to use Pythagorean's theorem here, along with the angle theta, to relate the sides of this triangle together if necessary. So let's see, what could we do? So to get the vertical component of the vector A that is perpendicular to line AA, all we have to do is take the magnitude of the hypotenuse of that triangle, so that would be A squared, subtract from it the square of the projection of the vector onto line AA, and then take the square root. We just used Pythagorean's theorem, but solved for the height component of the triangle. That's all we've done to find A perpendicular. Now, to find A perpendicular as a vector, we can simply take the total vector of A and subtract off the piece, the parallel piece that lies along line AA, and that would be the projection, not the projection, that would be the perpendicular component of the vector to the line. So all we did was rearrange the sum of the perpendicular and parallel components, which then create the vector A. We just rearranged that equation to solve for the perpendicular component of the vector. It helps to go back and look at the figure here as a triangle. Think about taking that A perpendicular and shifting it over to the right in order to understand what's going on with the equations. But then, of course, if you add A perpendicular with A parallel as vectors, you end up generating vector A.